Yeah, welcome to everybody who's joining our panel. So this is our panel on exploring complexity and how graph data science is pushing the boundaries. So just in terms of how the format and the agenda for the panel is going to work, I'm just going to do sort of 5 minutes of introductions, then going to do the bulk of the time will be spent on the panel where we'll be discussing various topics. And then we'll have a section at the end for Q&A. And we've also got a prize draw coming up at the end of this. So we have 3 tickets that we are going to be giving away for the Data Science Festival. And this is an online festival. There is also a physical opportunity happening in London at the end of November, but the online, we've got 3 online tickets to give away, and there's lots of talks there. So if you stick around to the end, we're going to have a random draw, and 3 lucky people will be able to get that. Just in terms of some of the logistics, we've got, if you have any technical issues you can't hear or something like that, please do use the chat for that. We have, somebody will be sort of monitoring that, but also just be respectful of what you kind of put in there and be mindful of others. If you want to ask the panelists any questions, if you can do that there's a Q&A section, what we'll do is we will collate all of those, and at the end we will try and go through as many of those as we can, group them together if need be, and then tackle it after that. So yeah, so that is just the logistics side of things. So welcome basically to everyone. Just give you a brief introduction to us and all the panelists. So my name is Nikki Watt, and I am the CEO and CTO here at OpenCredo, and we're hosting this panel today. And yeah, we're a hands-on software development company, which basically looks at helping clients to adapt and adopt emerging technologies to solve their business problems. So we work in a few different areas. There's platform engineering, cloud native, and also the data and graph space, which is really where the focus of this panel is going to be on. So I've worked with graphs for a while, and as has our sort of company on various different projects. And it's been fascinating, I think, over the years to see, you know, how some of the principles have remained the same, but actually there's been some changes and innovations as well, which have really sort of come about in the last few years. And that's what we are going to be talking about as we move forward. So I am delighted to have on this panel some really heavy hitters in the graph space. And I would like to introduce you first to Paco Nathan. So Paco Nathan is the managing partner at Derwen Inc., also known as a player coach, and he's got core expertise in data science, cloud computing, natural language, and graph technologies. With more than about 40 years technology experience. This has ranged from working in Bell Labs to early stage startups, also an advisor for Amplify partners, Recognize, Kung Fu.ai, and also lead committer on PyText Rank and KG Lab. So welcome, Paco. Really good to have you on board.
Thank you kindly.
Our second panelist is Dan McCreary. So Dan McCreary is a distinguished engineer and working for Optum Technology Collaborative. He works within the United Health Group to evaluate advanced technologies in AI, graph, and NoSQL. And Dan has a background in solution architecture, search, machine learning, and NLP. He's also the co-author of the book Making Sense of NoSQL, and was the co-founder of the Dataversity NoSQL Now series of conferences as well. So Dan is interested in hardware and software as well. In fact, I think Dan worked for Steve Jobs at Next and Bell Labs as an integrated circuit designer. So we're really interested to hear what's going on in some of the hardware and software space as well. So great to have you on board, Dan. And last but not least, we have Dr. Alessandro Negro, who's a real graph enthusiast, passionate about computer science, data research, and specializing in natural language processing, recommendation engines, fraud detection, and graph-aided search. He has a PhD in interdisciplinary science and technology, and actually previously founded a company called Reco4, which was an open source recommendation framework based on graph data sources. He is now the chief scientist at GraphAware, where he does a lot of work on Hume, which is an intelligent knowledge graph platform, speaking at various conferences as well, and also the author of the Manning book, Graph-Powered Machine Learning. So welcome to all of you. We are really excited to have you here and to learn more about graphs and innovations that are happening in this space. So what I thought we would do, and this is going to be the last slide I'm going to show, and then I'm going to put all of your lovely faces onto the screen so that we can have a conversation. But maybe just to start things off, I thought I would show a stat that I've seen popping up recently quite often in various different places, and it's actually a Gartner stat, which says that by 2025, 80% of graph technologies will be used in data and analytics innovations. And that's up from 10% this year. And if you also have a look at the hype cycle, which Gartner put together for AI, you can see that knowledge graphs are there at, they say, the peak of inflated expectations. I'm not sure if that's where we'd put them, but I thought what would be really good is to open up the discussion and just briefly discuss, like, why graphs? So why are graphs so well suited to doing complex data analysis in the spaces that we're going to be talking about? And, you know, where do knowledge graphs fit into that?
I just want to start out by commenting on this. This is amazing that Gartner has really made that statement, right? Right now, that only about 10% of companies are using graph technologies as a core part of their analysis, and that's going to jump to 80% in the next couple of years. That's really an amazing thing. Specifically, the big change I'm seeing is that when I would meet with analyst groups 2 or 3 years ago, we would ask them, well, what do you guys think the impact of GraphAware is? Many of them hadn't ever actually used graph. They hadn't actually built a graph. They hadn't actually talked to customers that had done this. And now they are all over it. They are really, really doing it. It's not just Gartner, it's the other analysts companies too. They're bringing on analysts that specialize in knowledge graphs and these things. So I'm just very impressed by the trend of analysts really picking these things up. I don't think they really had deep insights until they started to see a lot of these results from companies that were saving a lot of money. So it's a big trend, and the analysts are now starting to lead the way rather than be skeptical about these adoption techniques.
Fantastic.
We've seen over the past several years, there's been some great reports out of, say, Michael Chewy's group at McKinsey Global Institute, also out of MIT Sloan and others, about taking a look at which organizations are leading in terms of AI adoption versus ones that are finding some fetters, some challenges that impede them. And when you look across industry for enterprise, what are the key things that tend to block organizations? One of them that comes up consistently in that kind of analysis is about data being siloed and not being available across an organization. And I think that leads directly into what we're seeing here, the uptick on graphs, because it is so effective to do data integration across business silos. And I think that's kind of the thin edge of the wedge for a lot of graph applications, is just cutting across those divisions and making sense at a more global level.
Yeah, definitely. And if I can add a couple of notes on these, I think that really knowledge graphs will be the next big thing. After data warehouse, after data lake, I think that the knowledge graphs can really take the ownership, let's say, of doing what these two different approaches were able to do, because they added this semantic layer on top of the data finally, and this is a must to have if you would like to get concrete answers to your questions that were impossible, for example, in the data lake, in which you have no idea of the kind of data that you have there. So the type of analysis was very limited to just bulk processing. Here, with knowledge graph that added this understanding with metadata related to the data itself, allowed us to make a complex type of analysis that before were completely impossible to do because we didn't know what was in the data lake, for example. So apart from adding the data from different data silos, as Paco said, here we also are adding other information to describe this data in the knowledge graph, and this is really the real way to go if we would like to get concrete answers from the machines, instead of just getting a generic idea of what's inside the data. And that's the way in which graphs are really revolutionizing the field of artificial intelligence in the last, I would say, 5 years now.
Mm-hmm.
Yeah, I think just to answer your question very directly, why graphs, why now?
Yep.
And their answer is exactly what Paco says. It breaks down these silos of data. It provides an integrated view of whatever data we need. And in my experience, 70% of the time, it's an integrated view of our customers and all the touch points of our customers. So even though there's been a lot of use cases in Graph in the past, at the enterprise level, the leading use case for me and our groups that I work with is a single view of the customer we call Customer 360, and finding the really deep insights about who your valuable customers are and how to recommend products to them is really the leading use case that we're seeing.
And in terms of maybe just sort of picking up on that, having a graph kind of connecting all these different silos, are you finding that people are having to sort of manually collect things up, or is there some AI in actually kind of figuring out how to connect the data itself?
Well, it's interesting. I mean, it does bring in both challenges and benefits for data preparation parts of what you would think of as typical data science work. So, as a couple of concrete examples, detecting cycle detection, finding loops that probably shouldn't be in your data. If you're looking at your supply chain and you find that 2 of your worldwide locations just keep shipping the same widgets back and forth to each other, that's a problem, and it shouldn't exist, although in practice it exists way too much. So doing your data preparation so that it actually works with graph algorithms often involves a lot of graph algorithms to clean up the data and prepare it first. And another area close to what, or related to what Alessandro was talking about some is in terms of, say, transitive closure, where if you have that semantic view of your data, now you can start to fill in some of the blanks or identify where somebody should look very carefully, because clearly these parts don't quite fit and probably somebody needs to fix this data. And the thing is that we've been told for years that, don't worry about things like transitive closure and cycle detection because, oh, by the way, they're extremely expensive to do in a relational database. So usually we're steered away from doing these kind of workloads because, the rationale was, well, we just don't have the hardware to support it. And by the way, things have changed. We do have the hardware now.
Excellent.
And let me just add to this cycle issue, because recently we have a customer in which these cycles created a lot of problems in terms of applying other algorithms. Because, for example, the simple page rank, applied to graphs that have cycles could be heavily affected by them. So this is definitely true. Data preparation, it is definitely simpler in graphs, but it's fundamental, because otherwise your results will be completely affected in the wrong way, in this case, by these cycles. And this is just one of the examples, of course. But I totally agree with you, Paco, that this is the case. Before it was impossible to detect this cycle, and now with a simple query, you can get rid of all of them eventually. Or also applying other type of algorithms like, I don't know, minimum spanning tree, for example. It's a classic approach for just removing cycles before. And that's just amazing, how many algorithms you can pipe, all based on graphs techniques to get a better results at the end of the process that before was completely impossible.
Mm-hmm.
Yeah, I have one quick example just to describe some of the things that we're using Graph to this. And I should just emphasize, it's not just Graph, it's really parallel Graph. That is really being the big difference. The fact that in the past, things like entity resolution, if we were only running it on a single core of a single processor, we have a new record and we're trying to find out, should we link this to an existing record? those processes would just take forever and they would slow down our production systems. But now what we're seeing with parallel distributed graphs, and specifically FPGAs that do Levenshtein string fuzzy matching, we can get a very accurate distance calculation. Even if somebody mistyped 2 letters in a social security or a phone number, we can quickly get a distributed ranking and do entity resolution at scale in a much better way. And those, in my mind, one of the biggest costs of building a integrated view is taking these silos, bringing it together and linking them correctly together. And parallel graph is allowing us to do that.
I mean, maybe just staying on that subject. What are some of the sort of innovations that you're all seeing in the, doing graphs at scale? What kind of software and hardware innovations are taking place at the moment that you're seeing either with your customers that are really making a big impact?
Well, we do a lot of work with large firms in manufacturing, and some of the more complex issues, of course, that manufacturing contends with are supply chain, which has made the news over the past year or so, but is perpetually a problem in manufacturing, and also just industrial process understanding. Well, we have we're limited on being able to buy this particular kind of raw material. Maybe we could swap it out with something else. And when you're working with factories that are the size of small cities, swapping out a thing here or there has a lot of consequences. You have to understand about regulatory compliance and occupational safety and logistics and all that. So what graphs allow you to do are really to play a lot of these kind of business what ifs that would be inordinately expensive to compute otherwise. And I think that a lot of early business intelligence had really focused on aggregates. Let's take a look at quarterly sales. Let's roll up things to get more of an aggregate view. And graphs are going the opposite direction. We're really saying, okay, great, we've got our year-over-year sales metrics, but we're really concerned about this one plant that seems to be causing a slowdown across our global network. So can we drill down and look at the individual elements and their effects and isolate those? Because that's sort of like the next level of complexity for data analytics.
Great. Any thoughts on hardware sort of innovations or anything on that front?
Well, I'll just jump in because you guys all know I'm the hardware guy on the token hardware guy in the panel. Well, one of the biggest things about data science is that we have, I think, all found that the concept of a data lake has been very disappointing for a lot of our data scientists who are trying to quickly do analysis, because the data is just dumped there without really strong metadata and without connection data. We are finding that by loading things in a knowledge graph, our data science become different. They become knowledge science, right? Knowledge science is the art of finding insights on deeply connected, high quality data that's already analyzed for you, linked together, and has correct meaning. The schema is relevant and made explicit on writing to the graph, not on reading from the data lake. Mm-hmm. And what that does is it allows our data scientists to use this new collection of algorithms, and the most important of those being embeddings. The embedding movement is just an incredible piece that's happening, where instead of finding aggregates, as Paco was saying, we're focused on finding similarities. How do you find similar things, similar customers? Similarities at the heart of all recommendation and recommending the right products for people. So this embedding movement has been super important, because what it has done is it has put laser focus on one specific algorithm, and that's cosine similarity. Given a widget and 10 million other widgets, how do I find the 100 most similar widget? And can I do that in real time while a web page draws, the 50 millisecond goal? And the biggest thing we've all gotten through in hardware is the fact that cosine sim is pretty darn easy to implement in an FPGA. So just by adding one FPGA to your graph server, you can, in fact, find the 100 most similar customer or product or anything like that in a 50 millisecond window. And that's something that in the relational world, they just didn't even think about because it was so compute intensive. And now that's, I think, when you buy a product in the future, it's going to be hosted on a cloud server, and that cloud server is going to almost always have to have an FPGA that's tightly coupled into your knowledge graph to be able to do these things like find the most similar things. And that's going to really change the way that product managers reconceive the products that they want to build on these knowledge graphs. And I think once we get through the portability problem, we see all these fantastic problems that are doing entity resolution in hardware now, but they're not portable, right? Between our graph databases. And once we get to this GQL standard, this hardware is going to become prevalent, and it's just going to be a standard way to provision your servers when you build a cluster. And those servers are going to be scalable so that you can add more CPU and memory as your customer bases grow without ever shutting the servers down.
And yeah, I totally agree that the embedding is really the right way to go, even because, in that sense, the new algorithms were tested in the last few years. I'm thinking of more or less at the graph neural networks, for example, that are differently than the previous node to vex, for example, that was the leading solution. Here, they are taking into account also the different type of relationships. That is the main characteristic of a knowledge graph compared with a generic graph like the social network graph, because we have a different type of relationships and different type of nodes. And so now the most recent algorithms are taking into account the fact that we are connecting two different type of things instead of just people, for example, and we are connecting with different type of relationships. So these algorithms are now capable of capturing the real knowledge in a knowledge graph. That is a small difference, but it's critical because you can really model customers, you can model products, you can model even items in a supply chain, for example, in a different way. So this means that you can use this multidimensional projection of let's say of a graph in a way that of course similarity is the most common, but we are talking also about clustering, for example, or we are talking about regressions and this kind of stuff that are now possible because we can convert a graph that is embedding a knowledge in an embedded version of this knowledge that is easy to be managed in different ways. And then, of course, the hardware. I'm thinking also about the GPU evolution of the last years, for example, because many of these algorithms are leveraging this GPU rather than the CPU, for example. And now even our Macs can have these 32 core GPUs that can help us to make a simple computation that now is simple, but before was almost impossible. So, these are a couple of evolutions, I think, that changed a bit the way in which we are even just looking at the knowledge embedded in a knowledge graph. And this is opening tons of opportunities that before were just impossible for computational reasons, but also because we didn't know what to do with the graph. Now it's completely different because of this embedding, let's say, trend of ideas in this area.
I should just put in a plug. I think there was a really good book that just got published recently on graph machine learning by Manning on how to calculate these embeddings. So a little plug for that book there.
There's a lot going on, also taking advantage of different forms of hardware that are evolving. There's a lot going on at a layer just above. For the past 7 years or so, a lot of cloud computing, of course, has been very focused on Kubernetes and sort of a generation of cloud scheduling or scheduling resources within a cluster that's running in the cloud, let's say. But that is about to change, and there's a new generation of schedulers coming out that take into account, let's have a cluster where there are FPGAs, there are GPUs, we are sharing memory in very intelligent ways, such as Apache Arrow does. A lot of the rationale is that you know, if you're on a Kubernetes cluster, you're running something like Dask, you're going to hit a performance knee after you have a certain number of processing cores. And it's typically measured in thousands. And with the recent generations of supercomputing, of course, you can go much further. So there's a lot of work in progress now involving Stanford, Sandia Labs, Amazon, and NVIDIA to use a new generation of schedulers for the Pi data stack, where you can get out into tens of thousands of cores, mix and match with GPUs and FPGAs, et cetera. I think that that's what we're seeing in terms of really large scale graphs, like and financial, I think, is probably a pretty good example, and Alipay, where they're using systems like Ray, using futures, much more contemporary views of distributed systems for handling large graphs. And I think that a lot, my bias is Silicon Valley needs to catch up, because I think that a lot has happened at that hardware software interface that's still propagating out into the frameworks we use.
Interesting, very interesting. I mean, in terms of having sort of graphs operate at scale, I think over the last sort of few years and stuff, you know, people were having millions and then billions of sort of nodes in the graph, but we're getting to much bigger sort of sizes now. And you have even, you know, some of the graph database vendors, they're saying that they're dealing with, you know, sort of trillions of nodes and things like that. Is there anything that we need to sort of be aware of in terms of when we really kind of scale up past a certain sort of size that maybe even requires different sort of programming and stuff like that? Or any thoughts on that?
Yeah, well, physics definitely help. Go ahead, Dan. Sorry.
Yeah, I had a blog on this. Scale is a really, really hard thing to do for many products these days, especially if they weren't designed with scale from scratch. And what I like to do is get people to think about scale in 7 different dimensions. And it's not just data scale. That's the kind of the first one, but it's also things like compute scale. Can I upgrade my processors and some of my nodes continuously without rebooting the server? It's query scale. Can I add more and more queries to the system as the systems grow? Can I protect my data? So security scalability. Can I add more users that are only supposed to see a subset of that knowledge graph when you scale, and things like debugging. Can I make sure that many developers can all be writing their code concurrently without impacting the production systems? So what's a little crazy about this is the topic of enterprise knowledge graph, that word enterprise, is very attractive to many vendors. But even though they have products that don't scale, they are claiming their enterprise because they have one little feature that they think is relevant to that. Semantics is the most classic thing, right? Where they say, well, semantics makes you an enterprise graph. And I think what we need to do is be skeptical about some of those claims and really focus on much broader dimensions of, can I keep thousands of concurrent users all using the system, developing new queries, writing those queries, expand the system, have it be super high availability, not go down, and do those all concurrently. And when you start to build, we do have a lab that does simulated load stress testing, and we try to do all those things. 95% of graph products tend to fall over and die when you try to do those things. And even some of the best are still struggling on some of those areas. But I think what it's doing is it is really showing the way that we need to do. And I think some of the groups of people that are starting to do these benchmarks are really starting to show that we do need strong objective benchmarking at doing concurrent things, not just one algorithm, but making sure that we can run certain algorithms like PageNet during updates, where we have tens of millions of updates concurrently, because there's a lot of databases that could do very well in read-only, but they start to fall down when you do concurrent things. And in the real world, it's not a read-only world, right? It is a read-write world. So lots of my very strong feelings on scalability on vendor claims and enterprise capabilities. And
also, I think that one aspect that shouldn't be that should be considered is also the data model, because one of the aspects related to graphs is, of course, related to the fact that you can store the same set of knowledge, let's say, in this way, in tons of different ways. So even the best hardware will fall down if you cannot model your data in the proper way. And in this, you need really to know very well what's the entire stack that we are going to use, from the type of the graph database up to the hardware that we are going to use, because these will, let's say, affect enormously the way in which you can or you cannot model your data in a certain way in the graph. And this is fundamental. We notice too many customers really failing because they just decided at the beginning a graph data model that worked for a simple use case, and then they discovered that this could not scale up. Even with and we are not talking about a billion of nodes, we are talking about a very small example. But if poorly modeled, the graphs can just fail, because you can create easily dense nodes, for example, that some graph vendors struggle with. And really the model, apart from everything, should be in your mind constantly. And the nice part is that the graphs can evolve quite easily, but people still have these habits related to the relational databases, in which once you define your model, there is an entire set of books talking about how to migrate from one model to the other. That was painful. In graphs, this is not so painful. So really the graph model should be the right at first iteration, but you should keep changing it to fulfill all your needs. And as Dan said, you should consider that it's not a static graph. I mean, we are seeing how many graphs are constantly evolving because new data is coming in. So you need really to take into account many different things. And the model is what could save you or just cause your failure, in the graph adoption, for example. And then, of course, you need to take into account the hardware, the software that you are using, because this graph model will be affected by it. Different vendors, different approaches, for sure. For example.
Mm-hmm. I think one of the things that we find as well, slightly changing the subject a little bit, but related, is so the queries and being able to do the queries is great, but actually quite often business and enterprises, they need to be able to visualize, they need to be able to see what's going on in order to actually understand. And sometimes that in itself will end up changing the model and how they actually sort of do their queries and get the information that they need out of that. So I was wondering, do you have any insight onto the visualization side of things, some of the innovations happening there, in terms of either visualizing extremely large graphs or just making it easier actually to get the message of graphs and actually the benefit that they provide to companies through?
Well, certainly there's been a lot of innovations in terms of really large scale, high dimensional visualization work. I mean, using TSNE and other types of algorithms, UMAP, et cetera, to be able to get in and look at that kind of complex topology of data. So there's been some really good innovations on the algorithm side. But really, I think it comes back to hardware. We partner with a firm called GraphAware. So I'll shout out to Leo Marovich and company over at GraphAware. They've been doing a lot of GPU accelerated visualizations of large graphs. And it is startling because, we'll see, on a laptop, you can go up to so many nodes that you would put into a visualization before the whole thing falls over. And even if you have a cluster supporting you behind you with CPUs, you can only go so far. But when you have GPU-enabled visualization, I mean, this is what it was built for. And so you can get billion-node graphs that you can visualize and be interactive. And for enterprise, for somebody who's doing, say, market intelligence work, for them to make financial decisions by interacting with that scale of graph, it becomes, a real enabler to get the hardware engaged there.
Interesting.
I'll just throw my hat in the ring with the new open source low code visualization tools from Dash and Plotly. They're just revolutionizing thing. We used to use very, very expensive desktop tools, Tableau and a lot of the other commercial products. And they're pretty much gone out of our enterprise now. Everything is based on Python, right? This is the Python data science is driving the world. Python is the language of data science, and all the visualization tools are open source and freely available. And now we have some research projects to integrate some of the large language models, BERT and GPT-3 especially, so that people can just talk into a microphone or write down almost in a comment block of their Python code, and it's going to start to generate not just the graph query language, but the visualization tools in Plotly, and generate the widgets on the dashboards. And the biggest thing about this is having an enterprise tool so that those dashboards can be easily customized to the roles. You know, what we don't want to see is that everybody has access to everybody's data and everybody can build things on that. Having very precise role-based access of who can see dashboard widgets. And if those widgets are being generated multiple times, to cache the results, right? So caching of frequently used data sets. So maybe we generate a query once a night and those cache for the rest of the day. If people don't need the up to the minute things, you don't have to burden the graph. So integrated dashboards that are highly customized to roles, I think is a huge trend in visualization. And just what's crazy about this is the number of visualization widgets available in the Dash and Plotly ecosystem is just incredible now. And I'll just credit open source to a lot of that. There's so much creativity in open source, and people, when they're enthusiastic about their new visualization widget, they just put it out there. And it's really great to see some of that creativity.
Excellent.
Yeah, definitely. I would say that visualization is one of the most compelling issue in knowledge graph, specifically because, you know, the dimension. We have customers, for example, that just hate the hairball problem, you know, in the graph visualization. So definitely having a dashboard that could help you to see a portion of the data is one solution, and the other is just to give them predefined access patterns, for example, to start their analysis from a specific point of view, and go, you know, step by step to get the answers that that they need. I think that you know, really now there is plenty of solutions that could help you even to visualize the data from different perspectives. Some of them are graph related, but in this case, unfortunately, the hairball problem, as I said, is behind the corner. So really here, our responsibility as let's say consultants or developers is to help them to get the right access to the graph, because really many enterprises are just you know, look at the graph and they cannot see anything, and just small let's say nodes and tons of relationships. So in this case, we have the responsibility to give them the right patterns, you know, to access to these data in the graph visualization, in the dashboards. So this is where really they need some support, because otherwise they will be discouraged of not being able to visualize this data as they were doing before in the relational databases, for example. That was more common, you know, to visualize this data. Here, you know, the consultants or the professionals could play their role in helping them to access to this data, to these graphs actually in the proper way, and get the answers in the way in which they want. And the question and answer system will be definitely a right solution, you know, if we can provide some sort of a way for accessing to this graph, starting from a simple question in natural language, for example.
Mm-hmm, mm-hmm. I mean, so how does natural language NLP processing and stuff sort of help in this front in terms of building visualizations and the like?
I think Alessandro is the right guy to answer that question.
Yeah.
Go ahead.
Well, well, definitely we are. We did a lot of work in that sense to try to convert questions from from natural language in a query in knowledge graph. This is definitely one of the most relevant effort, that we could try to follow to shorten the distance between people and knowledge graph. Definitely, this is not a simple process because because of the richness of our languages and even the different type of questions that you can ask. But definitely, I see this as the next biggest potential, because if we look at the different approaches so far used for converting, let's say, questions in answers, very few of them are based on knowledge graph. So if we think about the knowledge graphs as our container, let's say, of our knowledge, well, once we will start to thinking how to convert in a proper way, our questions in queries, for example, and get not a string as in the classical question and answer system, but our concrete answers, well, that will play a key role in the really in the way in which we can make these knowledge graphs helping different type of customers, because only few people will be able to run a query, but anybody could just put a question in a form, for example, So definitely, this is the way to go. And my personal suggestion is since it appears to be a very complex problem, but the reality is that if we try to decompose this complex problem in many simplest step, well, actually, the way to go, it's much more reasonable in solving this complex problem. So that's the way in which I see the way in let's say, in which the customers, or ourselves, could help their let's say, their customers to get to a question and answer system that will actively query the knowledge graph.
Excellent. Right.
I just wanted to mention that I think if you haven't seen a demonstration of the Hume product that Alessandro has built in his team, it's a really good example of trying to make this complex thing of doing natural language queries and using NLP data much more accessible to the non-programmer, right? I think that's one of our challenges here, is that we have very good tools as long as you're a Python programmer, or as long as you know how to write graph queries. It is our job now to make it much more accessible. And I think what we're going to see is a whole new set of tools like Hume, and it's a really good example. There's some very good videos out there. You should just take a look at them. And it shows people who are not experts in Python and writing Cypher queries and things, actually being able to use these graphs and find deep insights. And that's one of the biggest trends, is to make graphs and these knowledge graphs, even though they're bigger and more complex and have very complex data models, because we don't have to worry about denormalizing. Everything is normalized. We have far more vertex types and attributes than we've ever had before, but we still need tools to make it easy to access. And I think that's one of our biggest trends that we're going to see, is a whole level of easy to access tools for non-programmers.
Yeah, I think that will be very important, because, as you say, not everybody knows how to write queries and program and all these side of things. So we are coming up. We're going to soon be approaching, I think, our Q&A time. But I want to give each of you just maybe a minute or minute and a half, if there's anything that you think you would. Your final thoughts, basically, on sort of graphs and innovation around there. What do you think is the next big thing to come up, or any parting thoughts from you before we go into Q&A?
Well, I think that, well, I would say the biggest challenge that we see amongst customers, it's more on the business side, not the technology side. I really do think that I mean, we've been, one of my colleagues, Jürgen Müller at BASF, Jürgen and I have been working on talks related to graph thinking and how to really conceptualize a business problem in terms of approaching it with graph technologies. And I think that there's a lot of cognitive aspects of that, sort of behavioral economics aspects of that. But when you can get a business unit leader to talk about their problem and start tracing out the flows and the conclusions on a whiteboard, almost inevitably they'll draw a graph. And when you can get them to start that dialogue, engaging with, the technology folks also about, well, here's actually this problem, here's a network analysis of how we would arrive at a solution. Why did we lose that customer bid? How can we track down the shipping manifest to find out? Things like that are hard problems that, weren't really addressable in relational data warehouses before. So when you can turn it around from a technology argument more to a business argument and start to get the business folks talking about it, I definitely find that enterprise IT shops have some reluctance to embrace graph technologies. So it's better to drive them from the business side. That would be my parting advice.
Fair enough. Fantastic. Dan, your thoughts?
I think the biggest thing we're going to start to see in the next few years is third-party applications that are portable across graph platforms. And I don't think we see a huge number of vendors doing that right now. They're very captive on one graph. So if I have an enterprise that has 6 different graph databases, I can only use it on the applications that have that one specific graph. And that's a real impediment, both for enterprise adoption of graph, as well as for third-party developers that want to build graphs. I think the GQL standard, which is, I think in the next year, we'll have a working draft of that. There's a research group in Europe that right now that's already got a sample that you can kick the tires on. But as that matures, we'll see an entire set of third-party applications that are portable across graph platform. That means that everything that we do today, every ERP system, every accounting system, every sales management system, all these AI applications for predicting sales, predicting your best customers, you're going to see this whole generation of portable value add solutions, not just underlying technology. And I think all of the things that researchers are doing today in the embedding movements and making data scientists more productive as being knowledge scientists are going to have a big impact on our things. I think it is going to transform the entire database industry, and the new generation of hardware that's custom tuned just to do pointer hopping at scale. I think 16,000 cores per chip. Those things are on the horizon too, and those are just going to accelerate it. Right now, most of the complex instruction set processes are very inefficient.
Mm-hmm.
Great, thank you. Alessandro.
Well, let me follow on these 2 amazing ideas. And really what I see in the future is that inside any big enterprise, we will see sitting on the same table, data scientists, business people, developers, everybody talking about graphs and knowledge graphs. And it will be a sort of common language that everybody can understand. And I mean, based on our experience, it will be the first time ever that we can sit on the same table and speak in a language that everybody can understand. Of course, from different perspectives, but everybody could understand it. And that will be even a communication channel open among the companies to get a better company on the long way ahead. So that's my hope and what I see in the future, because the simplicity of the graph, this is really behind the corner.
Excellent. All right. Well, I think thank you so much for that. It was wonderful to have such a good discussion with you all. We're going to go into the Q&A now. We've collated a few of the questions here. So I might throw some of them out there. So this one came from Dr. Steve Kramer. And he says, what are the best options with Python APIs available now for splitting dynamic graphs by period, example by hour or day, and then doing GNN-based anomaly detection in those evolving graphs?
Well,
I'll just jump in. I think any system that forces you to partition is really forcing you to optimize your graph for a specific query, and it's destined to failure. When you talk about reuse of that graph, for small project graphs, I think that's fine. I think as we focus on enterprise graphs, My understanding is that the more business units and the more different projects that can share the same knowledge, the lower the cost per business unit. So in my mind, we want to have a well-normalized model. And if that model can be shared across multiple business units, and they can all share that, then you shouldn't have to deal with the partitioning problem. So there's my tip.
Great.
Well, first off, hi, Steve. And also, I would typically, if somebody asked me this question, I would say, there's an expert named Steve Kramer you should probably talk with. I think that the problem of dynamic graphs is very interesting in the sense of, I mean, from a discrete standpoint, looking at how a graph is evolving, a graph representing some business processes for a large organization, for instance, or for a community of organizations, vendor relations, that kind of thing. Looking at how a graph is evolving over time is actually quite important. And sort of the discrete analysis of that dynamic graph, that evolution, can show you a lot of things, and is also very closely related to some of the work that we're doing with graph neural networks. But the continuous side of it is another problem altogether. Definitely some of the astrophysics people are pretty good in this. That's why I was referencing Steve, in terms of, understanding how do clusters look like, clusters of galaxies, how do they evolve over time? And there's a lot of math for that. Definitely the hardware is going to help. I am aware of a research project at Berkeley Rise Lab in terms of dynamic graphs, and perhaps also some similar work, related work over at ETH Zurich. I think that this is an area of research in AI that will see some work coming out of the labs over the next few years. It's a hard problem.
Great. Thank you. All right. So the next question we have, and please excuse me if I don't pronounce some of these names correctly. I think it's Itaria. So they write, we have built a knowledge management platform, Engage AI, that utilizes language embeddings, models, and knowledge graphs to help gather, organize, and reuse domain knowledge. We'd love to know your thoughts on domain knowledge management using knowledge graphs. Definitely graph supported embeddings help in there too, opens up virtuous improvement cycles. So I guess the question is your thoughts on domain knowledge management using knowledge graphs themselves. Not sure if I asked that correctly, or if Dilip wants to just speak that one out if I haven't.
I'll just throw in a real quick summary of when we work with people that are only interested in a single domain. Sometimes we find that they can't get the deep insights when they combine domains together at the enterprise scale. So very often teams, business units start out with a single domain modeling, but then they find that to find insights, they need to integrate that domain knowledge with the rest of the enterprise. So project graphs often evolve directly into a subdomain of enterprise knowledge graphs is the pattern we see over and over again.
I mean, one of the things about sort of domain knowledge and using that, I think that this strikes to where we have some approaches that are much more symbolic and leveraging inference based on semantics, very axiomatic. They don't work as well when you have really messy data, real world data, or continuous values. On the other hand, we have rule-based systems and probabilistic graphs. We can do things like probabilistic soft logic to assess how does a set of domain rules fit in this part of the graph versus that part of the graph, and do inference based off of probability, understanding causality. And then there's, purely empirical methods like deep learning. I would say not entirely purely, but close. So I think when you look at domain, you really have to take into account that there's a lot of different solutions. Some of them, they're really great if you have axiomatic properties on your data. But if you have absolutely none of that, maybe you shift into deep learning. But at the same time, let's take a look at uncertainty and measuring the probability of what you're trying to say based off of the domain rules. So I would foresee, I mean, what we do a lot with the KG Lab open source project is how do we bring a bunch of these kind of tools together into a pipeline so you can mix and match something that's strongly axiomatic with something that's strongly empirical and compare the results and find the delta?
And definitely, you need to involve domain experts, because again, people could be the very big difference, between machines, the pure machine approach, and the very good result that you can get involving people. And again, here knowledge graphs can play the role of simplifying the communication between machines and humans in this case, because they can, for example, be involved in a fast feedback loop, for example, adding new knowledge. So in this case, again, apart from the machines, humans can adjust your domain knowledge graph, for example, bringing their own knowledge inside the graph directly without passing through complex processes, because they can just add a relationship, for example, and saying that I don't know, a protein is connected with a gene, and nobody is presented or is represented with this information. So domain experts can really turn a quite good knowledge graph in a very good knowledge graph just by adding their information straightforwardly in the graph itself.
Excellent. All right. So I'm probably well, I'll have this next question, and maybe if we could try and answer it in 30 seconds to a minute, we can get 2 in there, and then we'll do our prize draw. So this is from Samir. So the question is, could you please explain the term knowledge graph? When does a graph become a knowledge graph?
Well, I stuck my answer in. The term knowledge, the way we define it in a lot of our systems, is it's connected information. Data is the raw bits. Information is when you identify the people, place, and things, and knowledge is when we connect people, place, and things. So it's a very general definition. And I think what we find is that there is a variety of terms, and the people that came from the semantic world insist that there has to be semantics. But in general, when we think of enterprise knowledge graph, it's really about breaking down silos and integrating it for a single connected high quality data view of our world.
Excellent. All right, I'm going to get one more in there, and then we will go on to our prize draw. So the final one is from Erlan, which is, could you share your opinion with respect to RDF versus LPG? Anyone want to stand that one?
Well, this will take more than 1 hour to discuss about.
A 1 minute version. You got a somebody said 1 minute.
Well, I think that there is no answer that will cover everything, but I really think that for my personal preference, LPG is just a bit, let's say, more compact way to represent the same set of information. That's why I generally prefer an LPG approach over the RDF, because representing the same information in RDF, for example, requires more connections and more things, and it's a bit verbose. But of course, the advantage in RDF is that you can use ParQL that is closer to the to the way in which you would query semantic networks, for example. That's my personal preference. So I will go for LPG just for compact version, and Cypher, for example, is now becoming another way of querying graphs and knowledge graph that could at some point get over the ParQL, for example. But my personal opinion.
All right. Well, we are running out of time, so I think I'm probably going to have to call an end to the discussion there. Thank you so much, all of our panelists. It's been fantastic, and thank you everyone for coming and attending. We hope to see you again at the next one.
Thank you.
All right. Thank you, everybody.
Bye bye.
Bye bye.